My name's Aaron Sloman. My first degree many years ago in Cape Town University was in physics and mathematics, and I intended to go and be a mathematician. I came to Oxford and encountered philosophers. I had started reading philosophy and discussing philosophy before then, and then I found that there were philosophers who said things about mathematics that I thought was wrong. So I gradually got more and more involved in discussions and switched to doing a philosophy DPhil. Then I became a philosophy lecturer, and about 6 years later I was introduced to artificial intelligence when I was a lecturer at Sussex University in philosophy. And I very soon became convinced that the best way to make progress in various areas of philosophy, including philosophy of mathematics, which I felt I hadn't dealt with adequately in my DPhil, but philosophy of mathematics, philosophy of mind, philosophy of language and other things, the best way was to try to design and test working fragments of mind and maybe eventually put them all together, but initially just working fragments that could do various things. And I learned to program, and with various other people, including Maggie Bowden, whom you've interviewed, helped to develop an undergraduate degree in AI and other things, and also began to do research in AI and so on, which I thought of as doing philosophy primarily. And then I later moved to the University of Birmingham, and I came there in 1991, and I've been retired for a while, but I'm not interested in golf or gardening, so I just go on doing full-time research, and my department is happy to keep me on without paying me and provide space and resources, and I come meeting bright people at conferences and try to learn and make progress if I can. One of the things I learnt and understood more and more over the many years, 40 years or so since I first encountered AI, is how hard the problems are. And in part that's because it's very often tempting to think the problem is something different from what it actually is, and then people design solutions to the non-problems. And I think of most of my work now as just helping to clarify what the problems are. What is it that we're trying to explain? And maybe this is leading into what you want to talk about. I now think that one of the ways of getting a deep understanding of that is to find out what were the problems that biological evolution solved. Because we are a product of many solutions to many problems, and if we just try to go in and work out what the whole system's doing, we may get it all wrong, or badly wrong. Well, first I would challenge that we are the dominant species. I know it looks like that, but actually, if you count biomass, if you count number of species, if you count number of individuals, the dominant species are the microbes. Maybe not one of them, but anyway, they're the ones who dominate in that sense. And furthermore, we are largely composed of microbes, without which we wouldn't survive. But there are things that made humans, you could say, best at various things, or you could say worst at various things, but it's a combination. And I think it was a collection of developments of which there isn't any single one. For instance, there might be some people who say the human language changed everything. By human language they mean human communication in words. But I think that was a late development from what must have started as the use of internal forms of representation, which are there in nest-building birds, in pre-verbal children, in hunting mammals, because you can't take in information about a complex, structured environment in which things can change, and you may have to be able to work out what's possible and what isn't possible without having some way of representing the components of the environment, their relationships, the kinds of things they can and can't do, the kinds of things you might or might not be able to do, and that kind of capability needs internal languages. With colleagues in Birmingham, I've been referring to them as generalized languages, because some people object to using the word language to refer to something that isn't used for communication. But from that viewpoint, not only humans, but many other animals developed abilities to do things to their environment to make them more friendly to themselves, which depended on being able to represent possible futures possible actions and work out what's the best thing to do. And nest building in corvids, for instance, crows, magpies, rooks and so on, is way beyond what current robots can do. And in fact, I think most humans would be challenged if they had to go and find a collection of twigs, one at a time, maybe bring them with just one hand, or your mouth, and assemble them into a structure that is shaped like a nest and is fairly rigid, and you could trust your eggs in when the wind blows. But they're doing it. And so they're not our evolutionary ancestors, but they're an indication, and that example is an indication of what must have evolved in order to provide control over the environment in that species. And I think hunting mammals, fruit-picking mammals, mammals that can rearrange parts of the environment, provide shelters, needed to have ways of representing possible futures, not just what's there in the environment. But I think at a later stage, that developed into a form of communication, or rather the internal forms of representation became usable as a basis for providing content to be communicated. And that happened, I think, initially through performing actions that expressed intentions and probably led to situations where an action, for instance, moving some large object, was performed more easily or more successfully or more accurately if it was done collaboratively. So someone who had worked out what to do might start doing it, and then the conspecific might be able to work out what the intention is, because that person has the same forms of representation and can build theories about what's going on, and might then be able to help. You can imagine that if that started happening more, a lot of collaboration based on inferred intentions and plans, then sometimes the inferences might be obscure and difficult. So the actions might be enhanced to provide signals as to what the intention is and what the best way is to help and so on. So this is all hand-waving, wild speculation, but I think it's consistent with a large collection of facts which one can look at. I'm fine if one looks for them, but one won't notice if one doesn't look for them, about the way children, for instance, who can't yet talk, communicate, and the things they'll do, like going to the mother and turning the face to point in the direction where the child wants them to look and so on. That's an extreme version of action indicating intention. Anyway, so that's a very long roundabout answer to one conjecture that the use of communicative language is what gave humans their unique power to create and destroy and whatever. And I'm saying, if by that you mean communicative language, then I'm saying there was something before that which was non-communicative language. And I suspect that non-communicative language continues to play a deep role in all human perception, in mathematical and scientific reasoning, in problem solving, and we don't understand very much about it. I'm sure there's a lot more to be said about the development of different kinds of sensors, the development of brain structures and mechanisms to support all that, but perhaps I've talked long enough on that question. Well, I think most of the human and animal capabilities that I've been referring to are not yet to be found in current robots or computing systems. And I think there are two reasons for that. One is that it's intrinsically very difficult. I think that in particular it may turn out that the forms of information processing that one can implement on digital computers as we currently know them may not be as well suited to performing some of these tasks as other kinds of computers about which we don't know so much. For instance, I think there may be important special features of chemical computers, which we might talk about later. But so one of the problems then is that the tasks are hard. But there's a deeper problem as to why AI hasn't made a great deal of progress on these problems that I'm talking about. And that is that most AI researchers assume things, and this is not just AI researchers, but many philosophers and psychologists and people studying animal behavior, make assumptions about what it is that animals or humans do. For instance, make assumptions about what vision is for, or assumptions about what motivation is and how motivation works, or assumptions about how learning works. And then they the AI people try to model, build systems that perform those assumed functions. So if you get the functions wrong, then even if you implement some of the functions that you're trying to implement, they won't necessarily perform the tasks that the initial objective was to imitate. For instance, the tasks that humans and nest-building birds and monkeys and so on can perform. I'll give you a simple example. Well, maybe not so simple, but it's often assumed that the function of vision in humans and other animals with good eyesight is to take in optical information that hits the retina and forming 2D, maybe changing, or well, in our case, definitely changing patterns of illumination where there are sensory receptors that detect those patterns. And then somehow from that information, plus maybe other information gained from head movements or from comparisons between two eyes, to work out what there was in the environment that produced those patterns. And that is often taken to mean where were the surfaces off which the light bounced before it came to. So you're essentially thinking of the task of a visual system as being to reverse the image formation process. So the 3D structures there, the lens causes an image to form in the retina, and then the brain goes back to a model of that 3D structure there. That's a very plausible theory about vision. And it may be that that's a subset of what human vision does. But I think James Gibson pointed out that that kind of thing is not necessarily going to be very useful for an organism, and it's very unlikely that that's the main function of perception in general, and they need to produce some physical description of what's out there. What does an animal need? It needs to know what it can do, what it can't do, what the consequences of its actions will be. So he introduced the word affordance. So from his point of view, the functions of visual perception are to inform the organism of what the affordances are for action, where that will mean what the animal, given its morphology, what it can do with its mouth, its limbs and so on, and the ways it can move, what it can do, what its needs are, what the obstacles are, and how the environment supports or obstructs those possible actions. And that's a very different collection of information structures that you need from saying where are all the surfaces. If you've got all the surfaces, deriving the affordances would still be a major task. So if you think of the perceptual systems as primarily for biological organisms being devices that provide information about affordances in that sense, then the tasks look very different. And most of the people doing research on computer vision and robots, I think, haven't taken all that on board. So they're trying to get machines to do things which, even if they were successful, would not make the robots very intelligent. And in fact, even the ones they're trying to do are not very easy to do, and they don't succeed very well. Although there's progress, I shouldn't disparage it too much. It gets more complex as animals get more sophisticated. So I like to make a distinction between online intelligence and offline intelligence. So for example, if I want to pick something up, like this leaf, I was able to select it from all of the others in there. And while moving my hand towards it, I was able to guide its trajectory, making sure it was going roughly in the right direction, as opposed to going out there, which wouldn't have enabled me to pick it up. And these two fingers ended up with a portion of the leaf between them, so that I was able to tell when I'm ready to do that. And at that point, I clamped my fingers and then I could pick up the leaf. Whereas And that's an example of online intelligence. During the performance of an action, both from the stage where it's initiated and during the intermediate stages and the way it's completed, I'm taking in information relevant to controlling all those stages, and the relevant information keeps changing. That means I need stores of transient information which gets discarded almost immediately and is replaced and so on. That's online intelligence. And there are many forms. That's just one example. And Gibson discussed quite a lot of examples, which I won't try to replicate now. But in offline intelligence, you're not necessarily actually performing the actions when you're using your intelligence. You're thinking about possible actions. So, for instance, I could think about how fast or by what route I would get back to the lecture room if I wanted to get to the next talk that's on. And I know where the door is, roughly speaking, and I know roughly which route I would take. When I go out, I should go to the left rather than to the right, because I've stored information about where the spaces are, where the buildings are, where the door was that we came out. But in using that information to think about that route, I'm not actually performing the actions. I'm not even simulating them in detail. The precise details of direction and speed and when to clap my fingers or when to contract my leg muscles when walking are all irrelevant to thinking about a good route or thinking about the potential things that might happen on the way. What would be a good place to meet someone whom I think frequents a particular bar or something. I don't necessarily have to work out exactly where the person's going to stand or from what angle I would recognize them and so on. So offline intelligence, which I think became not just a human competence. I think there are many other animals that have aspects of it. Squirrels are very impressive if you watch them, grey squirrels anyway, if you watch them in defeating squirrel-proof bird feeders. Seem to have a lot of that, as well as the online intelligence when they eventually perform the action they've worked out would get them to the nuts. And I think that what happened during our evolution is that mechanisms for acquiring and processing and storing and manipulating information that was more and more remote from the performance of actions developed. An example is taking in information about where locations are that you might need to go to infrequently. There's a store of a particular type of material that's good for building or putting on roofs or houses or something out around there in some direction. There's a store, good place to get water somewhere in another direction. There are people that you like to go and visit in another place, and so on. So taking in information about an extended environment and building it into a structure that you can make use of for different purposes is another example of offline intelligence. And when we do that, we sometimes use only our brains, but in modern times we also learned how to make maps on paper and on walls and so on. And it's not clear whether the stuff that's inside our heads has the same structure as the maps we make on paper. The maps on paper have a different function. They may be used for communication with others, or they're meant for looking at, whereas the stuff in your head you don't look at, you use in some other way. So what I'm getting at is that there's a great deal of human intelligence and animal intelligence which is involved in what's possible in the future, what exists in distant places, what might have happened in the past. Sometimes you need to know why something's as it is, because that could be relevant to what you should and shouldn't do in the future, and so on. And I think that there was something about human evolution that extended that offline intelligence way beyond other animals. And I don't think it was just human language, but human language had something to do with it. But I think there was something else that came earlier than language, which involves the ability to use your offline intelligence to discover something that has a rich mathematical structure. And I'll give a simple example. If you look through a gap, you can see something that's on the other side of the gap. Now, you might see what you want to see,
or you might see only part of it. If you want to see more of it, which way would you move? Well, you could either move sideways and see through the gap and see roughly the same amount, but a different part of what's on it, if it's a room or whatever. Or you can move towards the gap, and then your view will widen as you approach the gap. Now, there's a bit of mathematics in there insofar as you are implicitly assuming that information travels in straight lines. And as you go closer to a gap, the straight lines that you can draw from where you are through the gap widen as you approach that gap. Now, there's a kind of theorem of Euclidean geometry in there, which I'm not going to try to state very precisely, and as far as I know, it wasn't stated explicitly in Euclidean geometry. But it's something every toddler, human toddler, learns. Maybe other animals also learn it, I don't know. But there are many more things, actions to perform to get you more information about things, actions to perform to conceal information from other people, actions that will enable you to act on a rigid object in one place in order to produce an effect in another place. So there's a lot of stuff that involves lines and rotations and angles and speeds and so on that I think humans, maybe to a lesser extent other animals, developed the ability to think about in a generic way that meant that you could take out the generalizations from the particular contexts and then reuse them in new contexts in ways that I think are not yet represented at all in AI and in theories of human learning in any explicit way, although some people are trying to study the learning of mathematics. I wasn't going to challenge the claim that humans can do more sophisticated forms of tracking, just to mention that there are some things that other animals can do which are in some ways comparable and in some ways superior to things humans can do. In particular, there are species of birds and also, I think, some rodent squirrels, for instance. I don't know enough about the varieties that can hide nuts and remember where they've hidden them and go back to them. And there have been tests which show that some birds are able to hide tens, 80 or something nuts, and to remember which ones have been taken, which ones haven't. I suspect most humans can't do that. I wouldn't want to say categorically that no human could, because humans are very varied, and also people can develop particular competences through training. But it's certainly not something I can do. So. But I also would like to say that I'm not myself particularly interested in trying to align animal intelligences according to any kind of scale of superiority. I'm just trying to understand what it was that biological evolution produced and how it works. And I'm interested in AI mainly because I think that when one comes up with theories about how these things work, one needs to have some way of testing the theory. And AI provides ways of implementing and testing theories that were not previously available. Immanuel Kant was trying to come up with theories about how the mind worked, but he didn't have any kind of mechanism that he could build to test his theory about the nature of mathematical knowledge, for instance, or how concepts were developed from babyhood onwards and so on. Whereas now, if we do develop a theory, we have a criterion of adequacy, namely it should be precise enough and rich enough in detail to enable a model to be built. And then we can see if it works. If it works, it doesn't prove the theory is correct. It just shows it's a candidate. And if it doesn't work, then it's not a candidate as it stands. It would need to be modified in some way. I think there's a lot of optimism based on false clues. For example, one of the false clues is to count the number of neurons in the brain and then talk about the number of transistors you can fit into a computer or something, and then compare them. It might turn out that the
study of the way synapses work, which leads some people to say that a typical synapse, say in the human brain, has computational power comparable to the internet a few years ago because of the number of different molecules that are doing things, the variety of types of things that are being done in those molecular interactions and the speed at which they happen. If you somehow count up the number of operations per second or something, then you get these comparable figures. Now, even if the detailed statement is not right, there may just be a lot of information processing that going on in brains at the molecular level, not at the neural level. Then, if that's the case, then the processing units will be orders of magnitude larger in number than the number of neurons. And it's certainly the case that all the original biological forms of information processing were chemical. There weren't brains around, and still aren't in microbes. And even when humans grow their brains, the process of starting from a fertilized egg and producing this rich and complex structure is, for much of the time, under the control of chemical computation, chemical information processing, of course combined with physical sources of materials and energy and so on as well. So it would seem very strange if all that capability was suddenly thrown away when you've got a brain and all the information processing challenges were handed over to this brain mechanism. This is hand-waving on my part. I'm just saying that we might learn that what brains do is not what we think they're doing, and that the problems of replicating them are not what we think they are, certainly in terms of numerical estimates, or the timescales, the numbers of components, and so on. But apart from that, the other basis of skepticism concerns how well we understand what the problems are. I think there are many people who try to formalize the problems of designing intelligent systems in terms of streams of information thought of as bit streams or collections of bit streams, and they think of as the problems of intelligence as being the construction or detection of patterns in those streams, and perhaps not just detection of patterns, but detection of patterns that are usable for sending out streams to control motors and so on in order to achieve various goals. And that way of conceptualizing the problem may lead, on the one hand, to oversimplification, so that the things that would be achieved, if those goals were achieved, may be much simpler or in some ways inadequate for the replication of human intelligence or matching of human intelligence, or for that matter, squirrel intelligence. But in another way, it may also make the problems harder. It may just be that some of the kinds of things that biological evolution has achieved can't be done that way. And one of the ways that might turn out to be the case is not because it's impossible in principle to do some of the information processing on artificial computers based on transistors and other bit manipulating engines. But it may just be that the computational complexity of solving problems, processes of finding solutions to complex problems are much greater, and therefore you might need much larger universe than we have available in order to do things, than if the underlying mechanisms were different. The information processing mechanisms, they might be better tailored to particular sorts of computation. There's a very well-known example, which is finding the shortest route. If you've got a collection of roads, and they may be curved roads and lots of tangled routes from A to B to C and so on, and if you start at A and you want to get to Z, a place somewhere on that map, the process of finding the shortest route will involve searching through all these different possibilities and rejecting some that are longer than others and so on. But if you make a model of that map out of string, where the strings are all laid out on the maps and so have the lengths of the routes, then if you hold the two
knots in this network of strings which correspond to your start point and end point and just pull, then the bits of string that are left within a straight line will give you the shortest route, and that process of pulling just gets the solution very rapidly in a parallel computation where all the others just hang by the wayside, so to speak. Now, I'm not saying brains can build networks of string and pull them or anything like that. That's just an illustration of how if you have the right representation correctly implemented or suitably implemented for a problem, then you can avoid very combinatorially complex searches, which will maybe grow exponentially with the number of components in your map. Whereas with this thing, the time it takes won't depend on how many strings you've got in your map. You just pull, and it'll depend only on the shortest route that exists in there, even if that shortest route wasn't obvious from the original map. So that's a rather long-winded way of formulating a conjecture, which of supporting, a roundabout way of supporting a conjecture that there may be something about the way molecules perform computations where they have a combination of continuous change as things move through space and come together and move apart and whatever, and also snap into states that then persist. So as a result of quantum mechanics, you can have stable molecular structures which are quite hard to separate. They may need catalytic processes to separate them, or extreme temperatures or strong forces, but they may nevertheless be able to move very rapidly in some conditions in order to perform computations. Now, there may be things about that kind of structure that enables searching for solutions to certain classes of problems to be done much more efficiently by brains than anything we could do with computers. It's just an open question. Yeah. So it might turn out that we need new kinds of technology that aren't on the horizon in order to replicate the functions that animal brains perform. Or it might not, I just don't know. I'm not claiming that there's strong evidence for that. I'm just saying it might turn out that way. Partly because I think we know less than many people think we know about what biological evolution achieved. There are some other possibilities. We may just find out that there are shortcuts that nobody thought of, and it'll all happen much more quickly. I have an open mind. I'd be surprised, but it could turn out. There is something that worries me much more than the singularity that most people talk about, which is machines achieving human intelligence and perhaps taking over, running over the planet or something. There's what I call the singularity of cognitive catch-up. SOCC, singularity of cognitive catch-up, which I think we're close to, or maybe have already reached. I'll explain what I mean by that. One of the products of biological evolution, and this is one of the answers to your earlier questions, which I didn't get onto, is that humans have not only the ability to make discoveries that none of their ancestors have ever made, but to shorten the time required for a similar achievement to be reached by their offspring and their descendants. So once we've, for instance, worked out ways of doing complex computations, or ways of building houses, or ways of finding our way around, our children don't need to work it out for themselves by the same lengthy trial and error procedures. We can help them get there much faster. Okay, well, what I've been referring to as the singularity of cognitive catch-up depends on the fact that's fairly obvious and has often been commented on, that in the case of humans, it's not necessary for each generation to learn what previous generations learned in the same way, and we can speed up learning. Once something has been learned, we can speed up the learning by new people. And that has meant that the social processes that support that kind of education of the young can enormously accelerate what would have taken perhaps thousands or millions of years for evolution to produce, can happen in a much shorter time.
But here's the catch. In order for a new advance to happen, so for something new to be discovered that wasn't there before, like Newtonian mechanics or theory of relativity or Beethoven's musical style or whatever, the individuals have to have traversed a significant amount of what their ancestors have learned, even if they do it much faster than their ancestors, to get to the point where they can see the gaps, the possibilities for going further than their ancestors or their parents or whatever have done. Now, in the case of knowledge of science, mathematics, philosophy, engineering, and so on, there's been a lot of accumulated knowledge. And humans are living a bit longer than they used to, but they're still the limit of whatever it is, 100 years, or for most people less than that. So you can imagine that there might come a time when in a normal human lifespan, it's not possible for anyone to learn enough to understand the scope and limits of what's already been achieved in order to see the potential for going beyond it and to build on what's already been learned to make those future steps. So if we reach that stage, we will have reached the singularity of cognitive catch-up, because the process of education that enables individuals to learn faster than their ancestors did is the catching up process. And it may just be that we at some point reach a point where the catching up can only happen within a lifetime of an individual, and after that they're dead and they can't go beyond. And I have some evidence that there's a lot of that around, because I see a lot of people coming up with what they think of as new ideas, which they've struggled to come up with, but actually they just haven't taken in some of what was done by other people in other places before them. And I think that despite the availability of search engines, which make it easier for people to get the information. For instance, when I was a student, if I wanted to find out what other people had done in a field, it was a laborious process going to the library, getting books and going. Whereas now, I can often do things in seconds that would have taken hours. So that means essentially for that kind of work, my lifespan has been extended by a factor of 10 or something. So maybe that delays the singularity, but it may not delay it enough. But that's an open question. I don't know. And it may just be that in some areas this is more of a problem than others. For instance, it may be that in some kinds of engineering, we're handing over more and more of the work to machines anyway, and they can go on doing it. So, for instance, most of the production of computers now is done by computer-controlled machinery, although some of the design work is done by humans. A lot of detail design is done by computers, and they produce the next generation, which then produces the next generation, and so on. I don't know if humans can go on having major advances, so it'll be kind of sad if we can't. Okay, well, there are different branches of mathematics, and they have different properties. For instance, there's a lot of mathematics that can be expressed in terms of logical structures or algebraic structures, and those are pretty well suited for manipulation on computers. And if a problem can be specified using a logical algebraic notation, and the solution method requires creating something in that sort of notation, then computers are pretty good, and there are lots of mathematical tools around. There are theorem provers and theorem checkers and all kinds of things which couldn't have existed 50, 60 years ago, and they will continue getting better. But there's something that I was alluding to earlier when I gave the example of how you can reason about what you will see by changing your position in relation to a door, where what you're doing is using your grasp of spatial structures, and how as one spatial relationship changes, namely you come closer to the door or you move sideways in parallel to the wall or whatever, other spatial relationships change in parallel. So the lines from your eyes through to other parts of the room on the other side of the doorway change. They spread out more as you go towards the doorway, and as you move sideways, they don't spread out differently, they just focus on different parts of the internal, that they access different parts of the other room. Now, those are examples of ways of thinking about relationships and changing relationships, which are not the same as thinking about what happens if I replace this symbol with that symbol, or if I substitute this expression in that expression in a logical formula. And at the moment, I do not believe that there is anything in AI amongst the mathematical reasoning community, the theorem proving community, that can model the processes that go on when a young child starts learning to do Euclidean geometry and is taught things about. For instance, I can give you a proof that the angles of any triangle add up to a straight line, 180 degrees. There are standard proofs which involve starting with one triangle and then adding a line parallel to the base and doing things. But there's a much nicer proof that one of my former students, Mary Pardo, came up with, which I will demonstrate with this. Can you see it? If I have a triangle here, it's got 3 sides. If I put this thing on one side, let's say at the bottom, I can rotate it until it lies along another side, and then maybe move it up to the other end if needed. Then I can rotate it again until it lies on the 3rd side, and move it back to the other end. And then I rotate it again, and it'll eventually end up on the original side, but it will have changed the direction it's pointing in. And it won't have crossed over itself, so it'll have gone through a half circle, and that says that the 3 angles of a triangle add up to the rotation through half a circle, which is a beautiful kind of proof, and almost anybody can understand it. Some mathematicians don't like it because they say it hides some of the assumptions, but nevertheless, as far as I'm concerned, it's an example of a human ability to do reasoning, which once you've understood it, you can see will apply to any triangle. It's got to be a planar triangle, not a triangle on a globe, because then the angles can add up to more than... you can have 3 right angles if you have an equator, a line and an equator, and a line going up to the North Pole of the Earth, and then you have a right angle, and then another line going down to the equator. You have a right angle, right angle, right angle, and they add up to more than a straight line. But that's because that triangle isn't in a plane, it's on a curved surface. In fact, that's one of the differences, definitional differences you can take between planar and curved surfaces, how much the angles of a triangle add up to. But our ability to visualize and notice the generality in that process and see that you're going to be able to do the same thing even if the triangles are stretched in all sorts of ways, or if it's 1,000,000 times as large, or if it's made, written on if it's drawn in different colors or whatever. None of that's going to make any difference to the essence of that process. And that ability to see the commonality in a spatial structure, which enables you to draw some conclusion with complete certainty, subject to the possibility that sometimes you make mistakes, but when you make mistakes you can discover them, as has happened in the history of geometrical theorem proving. Imre Lakatos has a wonderful book called Proofs and Refutations, which I won't try to summarize, but he has examples. Mistakes were made. That was because people didn't always realize there were several subcases which had slightly different properties, and they didn't take account of that. But once they're noticed, you rectify that. But it's not the same as doing experiments in chemistry and physics, where you can't be sure it'll be the same on Mars, or at a high temperature, or in a very strong magnetic field. With geometric reasoning, in some sense, you've got the full information in front of you, even if you don't always notice some parts of it. So that kind of reasoning, as far as I know, is not currently implemented anywhere on a computer. And most people who do research on trying to model mathematical reasoning don't pay any attention to that, because that they just don't think about it. They start from somewhere else, mainly because of how they were educated. I was taught Euclidean geometry at school. Were you?
Yeah.
Okay. Many people are not now. Instead they're taught set theory and logic and arithmetic and algebra and so on. And so they don't use that bit of their brains, without which we wouldn't have buildings and cathedrals and all sorts of things that we now depend on. Well, this relates to what's meant by general. And when I first encountered the AGI community, I thought that what they all meant by general intelligence was uniform
intelligence. Intelligence based on some common, simple, maybe not so simple, but single powerful mechanism or principle of inference. And there are some people in the community who are trying to produce things like that, often connected with algorithmic information theory and compressibility of information and so on. But there's another sense of general which means that the system with general intelligence can do lots of different things, like perceive things, understand language, move around, make things, and so on. Perhaps even enjoy a joke. That's something that's not nearly on the horizon yet, as far as I know. Enjoying a joke isn't the same as being able to make laughing noises. Given then that there are these two notions of general intelligence, there's one that looks for some uniform, possibly simple mechanism or collection of ideas and notations and algorithms that will deal with any problem that's solvable. And the other assumes that you have something that's general in the sense that it can do lots of different things that are combined into an integrated architecture, which raises lots of problems about how you combine these things and make them work together. And humans certainly are of the second kind. We do all sorts of different things, and other animals also seem to be of the second kind. They're perhaps not as general as humans. Now, it may turn out that in some near future time, who knows, decades, few decades, you'll be able to get machines that are capable of solving in a time that will depend on the nature of the problem, but any problem that is solvable, and they will be able to do it in some sort of tractable time. Of course, there are some problems that are solvable but would require a larger universe and a longer history than the history of the universe. But apart from that constraint, these machines will be able to do everything. They'll have general intelligence. But to be able to do some of the kinds of things that humans can do, like the kind of geometrical reasoning where you look at the shape and you abstract away from the precise angles and sizes and shapes and so on and realize there's something general there, as must have happened when our ancestors first made the discoveries that eventually were put together in Euclidean geometry. It may be that that requires mechanisms of a kind that we don't know anything about at the moment. Maybe brains are using molecules and rearrangements of molecules in some way that supports that kind of reasoning. I'm not saying they are. I don't know. I just don't see any simple, any obvious way of trying to map that kind of reasoning capability onto what we currently do on computers. There is, and I'll just mention this briefly before finishing, there is a kind of thing that's sometimes thought of as a major step in that direction. Namely, you can build a machine, or a software system, that can represent some geometrical structure and then be told about some change that's going to happen to it, and it can predict in great detail what will happen. And this happens, for instance, in game engines, where you say, we have all these blocks on a table, and I'll drop another block, and then the thing uses Newton's laws and properties of rigidity of the parts and elasticity, and also stuff about geometry and space and so on, to give you a very accurate representation of what will happen when this brick lands on this pile of things and they bounce and go off and so on. You just, with more memory and more CPU power, you increase the accuracy. But that's totally different from looking at one example and working out what will happen in a whole range of cases at a higher level of abstraction, whereas the game engine does it in great detail for just this case with just those precise things, and it won't know what the generalizations are that it's using that would apply to other similar cases. So in that sense, you may get AGI, artificial general intelligence, pretty soon, but it'll be limited in what it can do. And the other kind of general intelligence, which combines all sorts of different things, including human spatial geometrical reasoning, and maybe other things like the ability to find things funny and to appreciate artistic features and other things, may need forms of types of mechanism that we don't know about yet. And I have an open mind about that.
Well, as far as the first type is concerned, could be useful for all kinds of applications. There are people who worry about whether a system that has that type of intelligence might in some sense take over control of the planet. Well, humans often do stupid things, and they might do something stupid which would lead to disaster. But I think it's more likely that they'll do other things that lead to disaster, like the population problem and using up all the resources, that destroying ecosystems and whatever. But certainly it'll go on being useful to have these calculating devices. Now, as for the second kind of thing, I don't know. If we succeeded in putting together all the parts that we find in humans, we might just make an artificial human, and then you might have some of them as your friends, and some of them you might not like, and some might become teachers or whatever, composers. But that raises a question, could they, in some sense, be superior to us in their learning capabilities, their understanding of human nature, or maybe their wickedness or whatever? These are all issues on which I expect the best science fiction writers will give much better answers than anything I can do. But I did once fantasize, when I wrote a book in 1978, that perhaps if we achieved that kind of thing, they would be wise and gentle and kind and realize that humans are an inferior species that, have some good features, so they keep us in some secluded, restricted kind of environment, keep us away from dangerous weapons and so on, and find ways of cohabiting with us. But that's just fantasy.
Awesome. Yeah, it's an interesting story of folded hands where the computers want to take care of us and wants to reduce suffering, and then ends up lobotomizing everybody. They're keeping them alive so as to reduce the suffering.
Not all that different from Brave New World, where it was done with drugs and so on, but different humans were given different roles in that system. Yeah. There's also the Time Machine, H.G. Wells, where in the distant future humans had split in two. The Elroy, I think they were called, they lived underground, they were the intelligent ones, and then the Morlocks lived underground. Elroy lived on the planet. They were pleasant and pretty, but not very bright and so on. And they were fed on by...
Yeah, it's a strange sort of future.
Yeah, as I say, if you ask science fiction writers, you'll probably come up with a wide variety of interesting answers.
Certainly have. I've spoken to Keith Stanley Robertson, Werner Vinge, Sean Williams, who else? And David Brin, all of which I've just interviewed recently.
Did you ever read a story by E.M. Forster called The Machine Stops? Very short story. It's on the internet somewhere. It's about a time when people sit in, and this was written about 1904, so it's about over 100 years ago. People are in their rooms, they sit in front of screens and they type things and they communicate with one another that way, and they never meet. They have debates and they give lectures to their audiences that way. And then there's a woman whose son says, "I'd like to see you." And she says, "What's the point? You can talk to me on this." But he wants to come and talk to him. I won't tell you how it ends.
It reminds me of the internet.
Well, yes, he invented. It was just extraordinary that he was able to do that before most of the components that we now need for it existed.
Another author that did that was Werner Vinge in a novella called True Names.
When was that written?
The 70s.
Okay, well, a lot of the technology was already off the ground then. The original bits of internet were working. In about 1973, I was sitting, from 1974, I was sitting at Sussex University trying to learn Logo, the programming language, to decide whether it was going to be useful for teaching AI. And I was sitting at a paper, teletype, with paper coming out, transmitting 10 characters a second from Sussex to UCL Computer Lab via telegraph cable, from there to somewhere in Norway via another cable, from there by satellite to California, to a computer Xerox Palo Alto Research Center where they had implemented a computer with a logo system on, where someone I had met previous year in Edinburgh was working, Danny Bobro, and he allowed me to have access to the system. So there I was typing. And furthermore, it was duplex typing, so every character I typed didn't show up on my terminal until it had gone all the way there and echoed back. So I would type and the characters come back 4 seconds later. But that was the internet. And I think Werner Wenger was writing after that kind of thing was already started, I think. But I don't know deeply. Anyway, right. I mentioned H.G. Wells, the Time Machine. I recently discovered, because David Lodge had written a sort of semi-novel about him, that he'd invented Wikipedia in advance. He had this notion of an encyclopedia that was free to everybody and everybody could contribute. It was a collaborative effort. So go to the science fiction writers and find out the future. Well, a range of possible futures.
Well, the thing is with science fiction writers, they have to maintain some sort of interest in the readers. After all, the science fiction which reaches us is the stuff that publishers want to sell.
Sure.
And so there's a little bit of a bias towards making a plot device there. And so the dramatic sort of appeal to our amygdala and lizard brain will sort of be there, obviously, be mixed in. But I think that they do come up with some amazing ideas.
Yeah.
I think it's worth trying to make these predictions. I think that we should focus more time on strategic forecasting. I mean, taking that seriously.
Well, I'm happy to leave that to others. I just want to try to understand these problems that bother me about how things work. And it may be that some would say that's irresponsible if I don't think about what the implications would be. Well, understanding how humans work might enable us to make surrogate humans. I suspect it won't happen in this century. I think it's going to be too difficult.
Well,
Okay.
thanks very much.